Okay, so this video is basically a quick overview of vocabulary and the concepts of probability that we will be covering in this algebra class. So the first concept to get under our belt is the different ways that you can express probability. There are three scales which are very familiar to you that are used to express it. The first one is the decimal scale, wherein probability that is extremely unlikely to occur is very, very close to zero, and something that is never, you are certain will never occur, would be a probability of zero. Something that is extremely certain would be approaching 1.0 or 1.0 in probability. A sure thing is 1.0. Now these scales might also be given in percent. Typically, this is the way that most probability is expressed. However, when you do calculations in probability, you will want to be having all the probabilities written in decimal, or the other form, which is fraction form. Fractions and decimals are the format that you'll be using for calculations. In fraction form, absolutely impossible would be 0 over 1. Absolutely certain would be 1 over 1. 50-50 would be 1/2. And of course, 50-50 comes from percent, 50%. As a decimal, it would be 0.5. In terms of certainty, a sure thing, in terms of certainty with percentages, is 100%. That's 1.0 as a decimal, it's 1 over 1 as a fraction, 100% certain. You probably have heard someone say that before. Okay, so in terms of notation, if you were trying to describe how likely it is that you are going to get the spinner to land on blue, it would be written P and then in parentheses blue. P, but the way it's read is the probability of spinning blue, the probability of blue. In this case, assuming that it's equally likely to land in any of these 8 quadrants, the probability of blue will be 1 out of 8. This is an example of theoretical probability because we are just saying that we think it's equally likely based on this being equal space. In real life, you might want to try experimental probability in this situation because you really don't know if all spinners are fair. Very often they're not, and you would want to do some experimental probability, which basically means you would just do an experiment, spin that spinner 100 times or 1,000 times, and find out how likely is it that you would get blue. If you spun it 80 times, you might expect to get around 10 blues. If you spun it 800 times, you might expect to get around 100 blues. The chance of not getting blue is its complement, or the complement of the chance of getting blue. It's basically the chance of getting the others. How many of them are there? There are 7 remaining spots. So the probability of not getting blue, in other words, the complement of getting blue, is 7/8, 87.5% as a decimal, 0.875. Either of these 3 ways, of course, would be perfectly fine for expressing that probability. In other words, it's vastly more likely that you would get a color other than blue than it is likely that you might actually get blue. Only 1 in 8 chance, 12.5% chance that you would get blue. All these numbers, incidentally, they must add up to a whole. 12.5% with 87.5%. With 0.875, it must be 0.125. They must add up to 1.0. And of course, 7/8 and 1/8, they will add up to 1.0. 2 other super important words to note are the words and the word or. These will come up in 2 different situations. When you say, what is the probability of spinning blue or red? That's a situation where it's one spin. And as you can imagine, the more colors you add, the greater the probability will become. It's one spin, there's 1 out of 8 that's blue, there's 2 out of 8 that are red, so you could say 1/8 plus 1/4, in other words 1/8 plus 2/8, therefore probability of blue or red is going to equal 3/8. The probability of not getting blue or red, of course, would be 5/8. Once again, that would be the complement if it was not. Now, and is a different deal. And makes it much, much less likely to occur. As you can imagine, you have to, in order to win, if this were a game, you would have to spin a blue, which is a 1 in 8 chance, and out of the only one time that that's going to occur, then you have to get extra lucky and you've got to get a red. So this becomes a situation where you are multiplying two fractions, not adding two fractions, because here clearly you're just adding extra options. It's going to improve your odds. This one, you're saying you have to get both things or none of it counts. And if you think about the complements, they really affect this. So the chance of getting blue, it's 1 in 8. The chance of getting red, it's 1/4. So the chance of getting blue and red, blue and blue is what I wrote. So blue and blue is going to be even less likely. So blue and blue will be 1/8 of 1/8. That's going to happen only 1 out of 64 times. It is 1/8 of 1/8. Whereas the probability of not getting blue 2 times in a row, so we were saying probability of not blue and not blue would be 7/8 times 7/8, which would be 49 over 64. So way better than half the time, better than even 2/3 of the time. It's pretty likely that you're not going to get blue in 2 spins. However, if you kept spinning, of course, it probably will increase that at some point you will get some blue. It's just not very likely to get blue and spin again and get blue again. When determining probability, it's super important to determine if the events in consideration are dependent events or independent events. How you make that decision is determining whether or not an outcome that happens, say for example, if you happened to pull out the ace of hearts out of the deck, and you did not replace that ace out of hearts back into the deck, would that affect the probability of pulling out the ace of hearts? Well, if it is simply one deck, there is simply one ace of hearts. If you do pull it out, the probability, and you don't replace it, the probability of getting ace of hearts is now 0. Probably beforehand with one deck, the probability is just 1 out of 52. But now when that one ace doesn't get replaced, it's now 0. 0 out of the remaining cards would be 0 out of 51. Still 0. If you are not replacing, that makes this dependent probability. If you put the ace back in the deck, in other words, if you are replacing, that makes these things an independent event. So whether or not you pull out an ace the first time has no bearing, no effect on the probability of pulling an ace out on the second time. If you were checking to see what's the probability of simply getting hearts, okay, so what is the probability of getting hearts? Well, it's 1 out of 4. Okay, it's also 13 out of 52. Same thing. But if you took out the ace and you did not replace it, now there is one less heart in the deck. That would make it 12. There's one less card in the deck. That would make it 51. This would be dependent probability because you are not replacing. Therefore, the probability of pulling out a heart has been changed.